Hello, this is Jihoon Ryoo. This is a makeup presentation for my previous thesis proposal in December of 2016. So I'm recording this video to give you the link for my oral presentation. Okay, I'm gonna start. Okay, welcome to my presentation. This is the Jihoon Ryoo. I'm going to cover towards batteryless communication for Internet of Things. Connect all things without battery. This is co-work with the EE department under the Smirdas. Okay, today more than 99% of the things in the physical world are still not connected to the internet. By the 2020, more than 50 billion devices will be connected to internet. So Internet of Things are very close to the future. So what's the bottleneck in terms of network researches? Connection. So connection is not free and consumes a lot of power. So IoT platform without battery is the future. Today I'm going to talk about this future. So I'm going to make the very realistic and futuristic platform for IoT devices. I will show you how we made and how it performs. Okay. Why is this wireless devices so power consuming? This is typical configuration of wireless devices. It usually consists of digital part and analog part. Analog part process the signals, then deliver the baseband signal to digital part, then digital do decoding and also generate the signal, then that generated signal is transmitted over the air through the RF. This digital part are power scaled with Moore's law. So over the years, it is improved very power efficient. So it only consumes microwatt level. On the other hand, the analog part does not have such scaling method. So it still consumes milliwatt level, which is too high to be work without battery. So we have to make a microwatt level. So let's take a look candidate radio for IoT platform. Legacy radio, which is usually used in Wi-Fi or Bluetooth, it consists of active transmitter and active receiver. Deliver this baseband signal. The transmitter generate analog signal. Then this analog signal is transmitted over the air. Then receiver decoding it. In terms of power, it consumes high power in transmitting and high power in receiving. Let's look at another candidate for IoT platform, the passive radio, which is usually used in AM and FM radio. To transmit this baseband signal, generate analog signal, then passive signal runs through the simple circuit and able to decode this baseband signal. Therefore, it consumes a lot of power in transmitting, but it consumes so small power in microwatt level in a receiving. Let's take a look another platform for future IoT platform. This is Backscatter Radio, which is commonly used in RFID. It consists of backscatter transmitter and backscatter receiver. Backscatter receiver provides carrier that can this baseband from transmitter of the backscatter can ride on that existing carrier. Then receiver able to decode this transmitted signal. In terms of power, it consumes very small power in transmitter since it is reflection and switching back of the transmitter, but it consumes heavy power in the receiver. So this is triangle of the current date. So this is future. We have to have very small power in TX and very small power in RX. Therefore, it can run without any battery. It runs only through collectible energies. So let's make an ideal radio based on the backscatter. Why is RX in backscatter is so power consuming? If you look at the Backscatter RX of the tag, it consists of carrier provider provide the carrier to write on the tags. Tag is backscattering devices, and also consists of the active IQ decoding. It usually has 10-bit ADC, which consumes milliwatt level. Let's take a look at the carrier provider. We force them divorce carrier provider from RX, then make designated carrier provider. So we make independent carrier provider. So they are divorced now. Alternatively, Wi-Fi or DTV, digital TV, can serve as carrier provider, but they are limited. Wi-Fi or DTV signal strength overwhelms the transmitted signal of backscatter. Therefore, TX and RX link is so limited in short ranges, under 3 meter, in the very nice environment. Realistically, install designated carrier provider works robustly. Since it is dummy device only provide the carrier, it can be implemented in low cost, under $20. It has no intellectual. So we force them divorce carrier provider and RX. So we have independent carrier provider. So RX has active IQ decoding and it consumes milliwatt power. So our approach is passive RX. Since backscatter signal is repeating high-low signals, which is 1 and 0, we can train circuit to provide reference value in between high and low. This is the typical RX of the backscatter. So reference level is circuit provide from the circuit, and then it is trained. Once it is high signal comes, it gradually increase. Once it is low signal, it's discharging. So it's charging and discharging by the 1 and 0 signals. Therefore, signal higher than reference decoded as 1, otherwise 0. So we make passive RX. This is only 1 bit from 10 bit in the active. So it is so it consumes such a small power in a microwatt level. Therefore, it is very nice. It is very good candidate for futuristic IoT platform. So there's new issue arise. Backscatter, since backscatter itself has very weak link, RFID overcomes with the channel hopping. What the channel hopping does is that it only able to channel 1, 3, 5. It jump to 1, 2, 3, 4, 5, 6. Then there is channel 2 and 4 is unable to communicate. It is characteristic of the backscatter. But what we want to do is a tag to tag, and it does multi-house, so it is not adequate to us. So link with the channel 1, it is disconnected, and link with the channel 2, so some nodes are isolated. So in our network environment, channel hopping is not efficient. Let's say link has knowledge on which channel will work, but have to transmit until connected. Because hopping channel is controlled by carrier provider, and it is random. If transmitter knows and able to determine channel for link, end-to-end network can be optimized. So we make transmitter able to choose communication link channel via channel selection. So introducing multi-phase backscatter IoT platform. Now transmitter has multiple reflection coefficient which work as multi-channel. So once carrier is provided, some of the channel is reflected. Therefore, once it is connected, it is high signal. Once it is not, it is low signal. So repeating 1010, controlled by the microprocessor that represent the baseband signals. So we are next generation communication platform for IoT. We called Button backscatter based tag-to-tag network. We make backscattering communication between tags, and we reassembled backscatter the communication for button, tag to tag. We make scalable communication system. In RFID, communication link is limited by the reader to tag link. And all the complex thing and providing carrier things, all the complex things are done in the reader side, and the tags are only dummy devices. Therefore, they achieve the battle-less communication, but they are not scalable. They only communicate under the 7-meter range, so have to install the many RFID reader to communicate. But we are scalable devices. We have independent carrier provider, so it can cover 20 meter in radius. Therefore, for example, in CS kind of environment, we may only need 2 or 3 CW provider, the carrier provider, then all network. They are IoT platforms which connected through the backscatter. They can be connected to internet. So we don't establish link between the CW provider and the IoT devices, but IoT device to device establish link, and some of them are selected as a leader and works as gateway. So they are connected to internet, so all the tags communicating through the backscatter, and they are also connected to internet. So this is our platform. This is the future platform for IoT devices. So let's take a look how it is performed. Button link performance. Over the distance, we measure the BER, bit error rate. So higher bit error rate is poor, lower bit error rate is good. So BER1 is every bit that I'm receiving is unable to decoding. BER10 raised by -4 is only 1 bit out of 10,000 bits are unable to decode. Means 10,000 minus 1 bits are able to decode. So over the distance, we have unreliable point, unable to communicate point. We call unreliable link. So our communication link is very limited, 1 meter, but we see we can communicate over 3 meters. But because of that peaks, we are unable to make clean communication link over long distance. So button performance in multi-channel. So since we are able to choose communication channel, so this is the BER with the channel 1 on the left, and on the right BER on the channel 2. They both have the unreliable link over up to 3 meter, but the peak position is different. So as we are able to choose, and once we pick the best channel through the simple routing algorithm, we are able to achieve 3 meter communication link. So we increase the CW carrier provider power, and we add more channel to transmitter. So channel 1 is the BER, and channel 2 and channel 3. As we are able to choose best channel, then we can achieve 10 meter radius communication link. So we also run the end-to-end packet error rate in real test bed. So we achieve lower than 100 packet error rate over the 4 hops. So we don't assume any unrealistic scenarios. This is very realistic scenario, and we performs very robustly. So introducing first generation of a button prototype. The face and the back, it consists of antenna and the transmitter modulator and RX detector, our passive receiver. It has a ultra low power microprocessor, which is MSP430. By replacing this MSP430 to Raspberry Pi, we can have gateway node. So it is connected to internet that can connect all the IoT devices to all the button devices to internet. So therefore we have IoT platform which consumes very small power in transmitter, very small power in receiving. So related work. We are not the first one who doing this. In SIGCOMM 13, there was ambient backscatter signal. They replaced the carrier provider to existing TV signal, but they only achieved 1 feet link range, and there is no multi-hop, so that is not scalable. In 2014 SIGCOMM, they had a Wi-Fi backscatter interconnect with the Wi-Fi devices through backscatter. So transmitting is Wi-Fi, and they mimic the backscatter behavior on the receiver side. They detect RSSI, then high and low, and a long term they achieved 100 bps, and they called Wi-Fi backscatter. And the BLE backscatter reader in RFID 15, they make backscatter signal for BLE devices decodable. So a typical Bluetooth device able to decode the backscatter signal. So turbocharging ambient backscatter in SIGCOMM 14, they made they used the full duplex communication with MIMO and network coding technology. So all the later works are assumed very research-based scenarios, but we don't assume any unrealistic scenarios, and we test it in real environment. So we need something more to be published in a nice venue. So future work, we adding BSI, backscattering state information. So we're going to investigate BSI for recognizing human activity. This platform is IoT to IoT link, IoT to IoT devices. So BSI is in between IoT to IoT link. So we're gonna measure how they are responding, how the channel is receiving, and how the channels are characterized based on the human activity. We believe this opens the door for performing large-scale activity analytics if such tags are widely deployed. So we done some work, and this is how it works, and we will going to do more to improve to make our paper stronger. So this is actual PSI channel reflection. In here we have 5 channels. So we segmented to channel, and we extracted channel features, we call phase features, and we also extract the power level, the DC level, and make feature. Then combining two of the features to the machine learning technology, then use for classification. So by now we achieve about 90 to 95% with the SBM based technology, and we are planning to use more. We are planning to use a CNN or any other neural network technology. Also, we are planning to collect more research participants and improve the accuracy too. Okay, thank you. This is my talk, and I hope you like this time.